This lesson will cover vertical transformations. The learning goal is to explore the effect of vertical stretches, compressions, reflections on the equation of a function and its graph. For success criteria, you can describe the transformations of a function based on its equation or graph, and you can create a graph of a transformed function. So a parent function with transformations of the form a times f of x, where we have k times x minus d plus c. Now we can also call this the general equation of a function. From the general equation, the variable a represents the vertical transformation. This is the vertical stretch or compression, as well as the reflection. Now there are several ways of graphing functions transformations. Most will use the parent function's shape points to determine the points of the transform function. So A has three different ways in which it's going to affect a graph. The first of which is when you're graphing a function in the form y of a times f of x, where a, the a itself, is a value greater than 1. Not necessarily looking at the sign. It can be -2, for instance, but it is bigger than 1. Now, functions of the sort where a is greater than 1, this is going to stretch the function vertically. So let's have a look at the base function, the parent function first. So the parent function is root of x. We know that the key points for root of x is 0, 1, 4. We're looking at perfect squares, and then we have the y equals root of x. That's our parent function there. So root of 0 is 0, root of 1 is 1, root of 4 is 2. Remember, we want to use the positive values here, otherwise we don't get a function. So let's plot these points. We have 0, 0, 1, 1, and 4, 2. Creating our curve, we now have our parent function for root of x. Now let's look at g of x here. So this is f of x right here. Let's do g of x. We'll change colors for this. So now we have g of x, and let's see how this affects our function here. So we can take the same values we have here. So there's actually two ways of doing this. We can create a new table of values using root of x as our left column and getting our new values from there, or we can create a table like this. So we can have x itself. X remains the same. Our x values stay as is. So we have 0, 1, and 4, and then we have now y equals 4 root of x. You can also rewrite this as 4y. That means we're taking these initial values we had and we're going to multiply them by 4. Because here, if we have, for instance, y equals a times f of x, if f of x is itself y, then we're multiplying these values by 4. So 4y, taken from this column, 4 times 0 is still 0, 4 times 1 is 4, and 4 times 2 is 8. So I'm taking from this column to grab this column here. I'm not taking from these values. What I'm doing is I'm taking I'm taking my parent function's table of values, and I'm manipulating these particular columns with my transformation. So I have my new points here. I have 0, 0, which doesn't change. I have 1, 4. And then I have 4, 8. Now 8 is going to be way up here. So this would be my function. Going way off the graph. So all of my coordinates, they are stretched vertically by a factor of 4. And we can see it here. So here we're looking at just the y values. My y value here is 0, multiplied by 4 is 0, so it stays where it is. Multiplying 1 by 4 gives us 4, which is where this stretch goes up to, and multiplying 2 by 4 gives us 8. So when you apply these transformations, you can do it from a table of values, or you can just look at the coordinates themselves and apply the transformations in that way. So when a is greater than 1, this is a vertical stretch. Now let's have a look at when our a value is greater than 0 but less than 1. So it has to be, it can be a decimal or a fraction between 0 and 1. I can't just say fraction because, if, for instance, I have 4 over 3. That's not less than 1. That has a different effect right there. So we're working with x squared now. So let's graph our parent function for x squared. We can just go ahead and plot this. And this time I'm going to go from the graph first. So let's say I had the graph to function, and I have g of x equals 1/2 of x squared. So 1/2 here, this means that I'm going to be multiplying my y values by 1/2. Let's change colors for this. Actually, first, I'll put the table of values in just so we can have that later on. So we have -2, -1, 0, 1, and 2. We have 4, 1, 0, 1, 4. Pretend that's not there, but we're going to use it in a bit. So here, let's say we had our coordinates, and we have a effect where we have 1/2 of x squared, so this halves our y values. We're going to take each coordinate and we can divide its y value by 2. So here, we have 2, 4, its y value divided by 2 is 2, so it'll be 2, 2. Taking this one here, dividing 1 by 2, that gives us 1/2. 0 divided by 2 is still 0, so this stays in the position. 1 divided by 2 is 0.5, and here 4 times 1/2 is 2. So this is our transform function. So that's as if I was looking at the points. But if we go back to table of values here, this 1/2 here is going to be affecting the y values as we saw. If we make a table of values, so this is 1/2 of y, our x values stay the same. -2, -1, 0, 1, and 2. And our y values, we're going to have each of these y values. So 1/2 of 4 is 2, 1/2 of 1 is 0.5, 1/2 of 0 is 0, 1/2 of 1 is 0.5, and 1/2 of 4 is 2. And that gives us the same points we had here. Now, if a is negative, so in this case I have -2, so it's going to be a stretch as well, but when a is negative, it's going to reflect our function in the x-axis. So this here is a reflection on the x-axis. So it has to specify which axis this is. Vertical reflection or reflection on x-axis, both the same way of saying it. So here, we again have x squared, so we have the parent function again. And let's get our table of values. This is we can work from both the graph and the table of values itself. So we have x and y equals -2 times x squared. So here x, let's again do -2, -1, 0, 1, and 2. And here we have, whoops, I want parent function, not the transform function yet. So here's x squared. We have 4, 1, 0, 1, and 4. Now let's get our transformed function now. So for our transformed function, again, our x values stay the same. It's still -2, -1, 0, 1, and 2. And our y values, so here, now we have -2 times y. So we're taking the y values and we're multiplying them by -2. So taking, again, these y values, -2 times 4 is -8, -2 times 1 is -2, -2 times 0 is just 0, -2 times 1 is -2, and then -2 times 4 is -8. And we can plot these points on our graph here. So 0 again stays the same. You'll notice that when you do reflections, or sorry, when you do horizontal vertical transformations, if you have a point on an axis, it is likely not to change. Especially the origin. The origin cannot be changed by vertical transformations. Only translations can move the origin. So we have 0, 0. We have -1, -2. 1, -2. And then we have 2, -8, which is way down here. And -2, -8. And then drawing a curve. And we have our transformed function. So while you're graphing, you can take your parent function and you can apply the transformations directly to the points visually. But what is recommended is that you take your parent function's table of values and you create a second table of values where you apply the transformations on your y or x variables depending on the transformations you have. So in summary, in general, the a value of a function is a vertical transformation. If a is negative, the graph is reflected on the x-axis. If the absolute value of a is greater than 1, you're vertically stretched. And if it's between 0 and 1, the graph is vertically compressed. So given any function, we can apply a vertical transformation to it. So in here, we don't exactly have a function based on the equation, but we just have this function right here. So given f of x, we want to sketch -2 times f of x. So -2 right here, this right here, this is a vertical reflection. And it's a vertical stretch by a factor of 2. So we have to take each coordinate, we need to reflect it on the x-axis and multiply its y value by 2. And you can do it in any order. So here, I can take this point, its y value is -1. So it would become -2 when I stretch it, and then it has to reflect on the x-axis, becoming +2. So this point here, its new location is above. Hopefully this graph doesn't delete my writing. And then we have this point here. It's at +2, so we can take its y value and multiply by -2. So 2 times -2 is -4, which is way down here. Or you can say, okay, I can reflect and then multiply by 2. So that also works. And then I'm going to connect the line here. It's not sticking there, so let's just keep them going. Here, it's +2, multiplied by -2 is -4. Or again, you can also flip or reflect on the x-axis and multiply by 2. Here, it's on 0. A coordinate on 0 where it's being vertically transformed is not going to be affected. It's going to remain in the same position because multiplying 0 by -2 still 0, doesn't change. And finally here, we can reflect and multiply by 2, or I say, okay, this is y value of 2 multiplied by -2 is -4, which is again down here. And then connecting our coordinates, so we have a transform function that looks like this. And hopefully that line stays there. If not, all right. Well, you saw for a moment, that would be our reflected function. Oh, sorry, our transform function.